Okay, let's unpack this. We use the web every single day. We tap a link, a video loads, we swipe, a page refreshes. It feels instant, or at least we get really, really annoyed when it isn't.
Oh, for sure.
But have you ever stopped to think about the absolute chaos happening behind the scenes to make that instant happen? I mean, the sheer, I don't know, violence of it.
Violence is actually the right word. It is a fascinating ecosystem. And you're right, we just take it for granted.
You do.
But if you look under the hood, the history of the web isn't just a history of, better websites or nicer fonts. It's actually a 30-year war.
A war.
A war on latency. It's this constant, invisible battle against the laws of physics, the speed of light, and the limitations of the networks we built decades ago.
I love that framing. And today we are looking at this really cool visual titled The Evolution of Web Protocols.
Yeah, it's great.
It's basically a timeline, but instead of dates on a calendar, it looks like a pipe that's mutating over time.
Yes.
So on the far left, back in 1991, you've got this rusty, thin little wire with a basic plug. It looks like something you'd find in a derelict basement in the 80s.
Right.
And then as you move right, it grows. It gets armor, it gets gauges, and by the time you hit the present day, it looks like this futuristic sci-fi laser blaster firing multiple beams at once.
That visual is perfect because it illustrates the shift in mission. In the beginning, 1991, the web was just a document retrieval system. You wanted a file. Here's the file. Done. But today, the web is a high-performance application delivery platform. We are streaming 4K video, we're collaborating in real time, gaming. The pipe had to change because the water flowing through it changed completely.
So let's go back to that rusty wire.
Yeah.
1991, HTTP 0.9. The source material calls this the one-line era. Why one line?
Because it really was just one line. It's almost hard to believe now.
Literally.
Right.
If you wanted to visit a page, your computer would send a command that looked like GET hello.html. That's it.
Simple, right? No headers, no version numbers, no metadata. It was raw. You couldn't even tell the server what kind of content you accepted. It was just, give me this.
The design philosophy listed here is just simplicity, a raw pipe for data.
Which was fine for the time. You ask for a text file, the server sends the text file, and then, and this is the crucial part, the server hangs up.
Right, the immediate disconnect.
Exactly. The server sends the HTML and immediately closes the connection. It wipes its hands of you.
So if I want another file, or if that page links to something else,
You have to dial again.
that seems incredibly inefficient.
It wasn't a problem when a website was just a single text file, maybe one image if you were feeling wild.
Sure.
But websites didn't stay simple for long. By 1996, we get HTTP 1.0, and the sources call this the metadata explosion.
Yeah, looking at the diagram for 1.0, it suddenly looks like a real conversation. We aren't just saying VT file. Now we have headers. We have status codes.
This is huge. For the first time, the server could actually talk back. It could say 200 OK, meaning I found it, or the infamous 404 not found.
Right.
We could also tell the server what kind of browser we were using with the user agent header, or what kind of data we were sending MIME types.
So we could finally send images, video, and rich media.
Yes. But here is the catch. While we made the content richer, we didn't fix the plumbing. The plumbing was actually catastrophically inefficient.
We were still hanging up the phone.
We were still hanging up the phone. Imagine having a conversation with a friend, but after every single sentence, you have to hang up and call them back to say the next sentence.
That would be maddening.
That was HTTP 1.0. If a website had 10 images, your browser had to open a connection, download image 1, close the connection, open a connection, download image 2, close the connection, 10 times.
Okay, so let's unpack why that is such a big deal. I mean, computers are fast. Does redialing really take that long?
This is the single most important concept to understand about web performance. We have to talk about the villain of our story. The cost of reliability.
We're talking about TCP.
Transmission Control Protocol. The web is built on top of TCP. Now, TCP is great because it ensures that when you download a file, you get the whole file in the right order without missing pieces.
Right.
But that reliability comes with attacks.
The handshake.
The handshake. Before you can send a single byte of that cat picture, your computer and the server have to agree to talk. It's a 3-step process.
A negotiation.
Your computer sends a SYN packet, basically saying, hello, can I speak? The server sends back a SYNAC, yes, I hear you, can you hear me?
Okay.
And finally, your computer sends an ACK, I hear you, connection open.
And only then can you actually ask for the file.
Correct. That's 3 trips across the wire before any data moves. In networking, we call that the round-trip time, or RTT.
I love the analogy the source uses here, the garden hose analogy.
It's the best way to visualize it. Think of the data as water and the TCP connection as a hose.
Okay.
You cannot water the garden until you unroll the hose. That unrolling is the handshake.
And in HTTP 1.0, because we disconnect after every file.
You are rolling the hose back up after every single drop of water. You unroll it, spray 1 drop, roll it back up. Unroll it, spray 1 drop, roll it back up.
That is painfully inefficient. You're spending 90% of your time messing with the hose and 10% actually watering the plants.
Exactly, and that is why the web felt slow, even as internet speeds got faster. The latency of the handshake was killing us. It's a physics problem. It takes time for light to travel from New York to London and back 3 times.
So enter HTTP 1.1. The year is 1997. The solution seems pretty obvious in hindsight. Stop rolling up the hose.
We call it connection persistence, or keep alive. It was a game changer.
How'd it work?
The idea is simple. You do the handshake once, you unroll the hose, and you leave it unrolled. You request the HTML, get it. Then, using that same open connection, you request image 1, image 2, image 3.
So instead of 3 requests taking 9 round trips of handshaking, you just do the handshake.
Once. A massive performance boost. It saved the web in the late 90s. But human nature being what it is, as soon as we got faster, we built heavier websites.
We just fill the pipe with more stuff.
And that revealed a new bottleneck. Even with the hose unrolled, HTTP 1.1 was sequential. You ask for a file, you wait for it. You ask for the next one, you wait for it. It's a FIFO queue, first in, first out.
This brings us to the grocery store problem. I think everyone has experienced this in real life.
Oh, it's the perfect analogy for what we call head-of-line blocking. Imagine you are at the grocery store checkout. You are standing there with just a pack of gum.
Right, a tiny little thing.
That represents a tiny 1 KB JSON file that your website needs.
But the person in front of me.
The person in front of you has a massive cart overflowing with items. That's a 5 megabyte high-res image.
Of course.
In HTTP 1.1, you have to wait for the cashier to scan every single item in that massive cart before you can pay for your gum.
Waits 501 milliseconds, the diagram says.
Even though your transaction would take 1 millisecond, the bandwidth is there, the cashier is working. But the tiny file is blocked by the big file at the head of the line.
So the browsers, Chrome, Firefox, or I guess Netscape back then, they decided to cheat, didn't they? This part of the timeline shows browser hacks.
We call it a workaround, but yes, it was a hack. Browsers realized that waiting for files one by one was too slow. So they decided, if the line is too long, let's just open more checkout lanes.
The chart shows 6 parallel TCP connections per domain.
Right. Instead of 1 hose, the browser opens 6 hoses to the same server, just brute forcing the bandwidth.
It's like instead of 1 checkout lane, they forced the store to open 6 just for them.
Which helps, but there is a hidden cost to opening new connections that we haven't discussed yet. It's called TCP slow start.
Oh, I saw this graph in the notes. It shows a line that starts low and zigzags its way up. It says a colder connection is slow, but a warm connection is fast. Why does a connection have a temperature?
It's a safety mechanism. Think about it. When you first connect to a server, the server doesn't know how fast your internet is. Are you on a 5G fiber line? Or are you on a dial-up modem in a rural basement?
It has no idea.
If the server just dumps 10 megabytes of data on you instantly, and you're on a slow connection, it will clog the network, packets will jam up, and everything crashes.
So it dips a toe in the water.
Precisely. TCP treats every new connection as a risk. It starts by sending a tiny amount of data. If your computer acknowledges it, I got it, the server doubles the amount. Then it doubles it again.
And it keeps ramping up.
Keeps ramping up until it hits a limit congestion and packets start dropping. Then it backs off.
So a new connection spends the first few moments just trying to figure out the speed limit.
Which is why those parallel connections the browsers were opening were actually inefficient. They were all cold. They all had to go through that slow start phase.
Oh, okay.
The best scenario is actually one single warm connection that's already running at max speed.
But we couldn't do that with HTTP 1.1 because of the grocery store problem. If we use one connection, the guy with the gum gets stuck.
Exactly. We were stuck between a rock and a hard place. Parallel connections were a messy hack. We needed a real solution.
Enter HTTP 2. The year is 2015.
Finally.
The visual here changes completely. The pipe isn't just a pipe anymore. It's filled with these colorful little interlocking blocks, it looks like. I don't know, Tetris inside a tube.
That is multiplexing. This is the binary shift. Before this, HTTP was text human readable. You could open it in Notepad and read it. HTTP2 chops everything up into tiny binary frames.
So instead of setting the big red block, the image, all at once, it chops it into little red bricks. And it chops the blue block, the CSS, into little blue bricks.
And then it mixes them together. It interleaves them. So the server sends a few chunks of the big image, then slips in the tiny JSON file, then goes back to the image.
So the guy with the gum doesn't have to wait. He just squeezes in between the items in the big cart.
Exactly. We solved the application ahead of line blocking. We could finally use one single warm TCP connection for everything.
And there's another efficiency trick here called HPACK, header compression.
Oh, this was long overdue. Remember those headers we talked about in HTTP 1.0, user agent, Mozilla 5.0, and all those cookies?
Yeah, the metadata.
In HTTP 1.1, your browser sent that same massive block of text with every single request.
So if a page has unthreaded images, I'm saying, hi, I'm using Chrome 100 times.
Yes. Massive redundancy. It was just clogging the pipe. HTTP2 is smarter. It maintains a state table. It remembers what you sent last time.
Okay.
So for the second request, instead of sending the whole string, it just says, hey, use value number 84 from the table.
That's so much smarter. So HTTP2 sounds perfect. We have one warm connection, we're mixing data so nobody waits, and we're compressing the repetitive stuff. Mission accomplished, right?
You would think so. But remember, this is a war. And just when you think you've won, a new enemy appears. Or rather, an old enemy reveals himself.
The recurring villain, TCP head of line blocking.
We made a strategic error. We moved all our traffic into one single TCP connection to make it efficient. We put all our eggs in one basket.
And if you drop the basket?
Here is the tragedy. TCP guarantees in-order delivery. Imagine those colored blocks flowing through the pipe. Packet 1, Packet 2, Packet 3. If Packet 2 gets lost in transit, maybe you walked behind a concrete wall or the signal flickered,
Right.
the computer receives Packet 1 and Packet 3.
But it can't process Packet 3.
No, the operating system says, wait, I am missing number 2. I cannot give you number 3 until I get number 2.
Even if Packet 3 is a totally different file. Like if Packet 2 was part of the image, and Packet 3 was the CSS for the buttons.
It doesn't matter. TCP doesn't know what an image or a button is, it just knows numbers. It's blind to the content, so the entire connection freezes. Everything stops. The image, the text, the buttons.
Wow. That is tragic irony. By fixing the grocery store line problem at the application layer, we actually made the website more fragile at the network layer.
Correct. On a spotty network, HTTP2 can actually be slower than HTTP 1.1, because in HTTP 1.1, if one connection stalled, the other 5 kept going.
But in HTTP 2,
If the one connection stalls, the whole world stops.
so what do? We can't fix TCP. It's baked into the operating systems of billions of devices. It's in the kernel.
That's right. TCP is ossified. Middle boxes, routers, firewalls, they all expect TCP to behave a certain way. If you try to change how TCP works, the internet's infrastructure will just block your packets. You can't just change the rules of TCP overnight.
So we went for the nuclear option.
HTTP 3. And the protocol underneath it, QUIC.
And the big headline here, we abandoned TCP.
We switched to UDP.
Now, for those listening who know a bit about networking, UDP is usually the unreliable one, right? It's the protocol used for things where it doesn't matter if you lose a packet, like streaming voice or video games.
That's the reputation. UDP is a fire and forget protocol. It doesn't do handshakes, it doesn't guarantee order, it just throws packets at the wall.
So how can we build the secure, reliable web on that? We need the website to load correctly.
That's the genius of QUIC. It takes that basic, raw UDP protocol and it rebuilds all the safety features, reliability, congestion control, encryption, but it builds them in user space on top of UDP.
User space. Help us visualize that.
Imagine you want to renovate your house, but the city, the operating system kernel, has strict zoning laws, TCP, that haven't changed in 30 years. You can't move the walls.
Okay.
QUIC is like building a completely new modular house inside the living room of the old house. You don't ask the city for permission. You just use the empty space UDP to build your own rules.
So instead of relying on the operating system to handle the safety, the browser does it.
Exactly. This bypasses the clumsy kernel mechanisms, and because we're building the rules from scratch, we can fix the eggs in one basket problem.
The visual here shows train tracks. This connects to the true independence concept.
In TCP HTTP2, it was one single track. If the train broke down, everything behind it stopped. In QUIC, every stream of data, the image, the CSS, the JS, has its own independent track.
So if a packet for the like button gets lost,
The main video keeps playing. The streams are independent. The browser says, oh, I missed a piece of the button. Fine, I'll wait for that piece, but let me show the user the video right now.
That is a massive shift. It's like we finally realized that the network layer shouldn't be dictating the user experience.
And it gets even better when we talk about mobility, because let's be honest, the modern web isn't a desktop computer plugged into a wall. It's a phone in your pocket.
Right. We aren't sitting at desks anymore. We are walking around.
And when you walk out of your house, you switch from Wi-Fi to 5G.
And when you do that, your IP address changes.
In the old world of TCP, a connection is defined by your IP address. If your IP changes, the connection is dead. You have to start over. Handshake, slow start, encryption negotiation, everything.
That's why sometimes when you leave the house, your music creates that awkward pause or the web page hangs for a second.
Exactly. But QUIC introduces connection migration.
How does that work?
Instead of using your IP address to identify you, QUIC assigns a connection ID, a UUID.
It's like a name tag.
Yes. So when you switch from Wi-Fi to 5G, your phone just sends a packet from the new network saying, hey, it's still me. Here's my ID. The server says, oh, hey, keep talking.
No handshake.
No handshake, no interruption. The connection survives the network change.
That is incredible. And looking at the speed comparison, the handshake itself is faster too.
Much faster. TCP plus TLS, the security layer, took 3 round trips to get started. QIC combines the handshake and the security into one step. It's often just 1 round trip, sometimes 0.
0 RTT.
If you've talked to the server before, you can sometimes send the request with the first hello. Hi, it's me again. Send the file right now.
It feels like we've finally reached the sci-fi blaster end of the pipe.
We really have. We've turned a simple pipe into a smart delivery system.
Let's wrap this up with the summary table because it really crystallizes the trade-offs we've made over the decades.
Sure.
We started with transport. We went from text in HTTP1 to binary TCP in HTTP2 to UDP and QUIC in HTTP3.
Right. Moving away from human-readable protocols that were easy to debug to highly optimized binary ones that are incredibly efficient.
Multiplexing.
None in version 1. We had it in version 2, but it was flawed because of TCP blocking. In version 3, we finally have true independent streams.
And encryption.
This is a key point. In HTTP1, encryption was optional. In HTTP2, it was de facto mandatory because browsers required it.
Wow.
In HTTP3, it is baked in. You cannot do QUIC without encryption. It's built into the handshake.
So what does this all mean for the big picture? Why should the listener care about this engineering gymnastics?
Ideally, it means the user never notices any of this. It just works. But for us, understanding the history, the takeaway is that we have moved complexity from the network stack into the application layer.
What do you mean by that?
In the 90s, we trusted the network to handle the delivery, TCP, and we just sent text. Now, we don't trust the network. We assume the network is hostile, unreliable, and mobile.
Right.
So we built a protocol, QUIC, that handles reliability, congestion, and security inside the application itself. We took control back.
The one-line protocol is now a sophisticated, independent stream engine.
Precisely. It's a war on latency, and we're finally winning.
So, the next time you are listening to this deep dive and you walk out your front door, switching from your home Wi-Fi to your data plan without the audio skipping a beat, take a second to appreciate the sheer amount of engineering history that just happened in your pocket.
It's the invisible war, winning a battle right there in your hand.
Thanks for joining us on this deep dive into the plumbing of the web. It's wild down there.
Always a pleasure.
Catch you next time.